I think I dared looking.
If you remember back in the very beginning, probably our very first lesson of school, we classified numbers as like natural, whole, integer, rational, and real. These are not real numbers. So if you remember, there was like a box, we had like real numbers, and then we had rational, irrational, and then within the rational we had natural, whole, and integers as well. We're actually looking at imaginary numbers, which are not real numbers. Okay, so they're not actually going to show up in the real number space. They're different. The reason we're learning them is that whenever we are looking at a quadratic and we see a graph on a graphing calculator that looks like this, and we're asked to solve it and find the zeros, which is, of course, where it crosses the x-axis. When you're looking at this, well, it doesn't cross the x-axis, right? So the answer to this would be no real solutions, okay, if you were solving it. But there will be numbers that involve imaginary numbers in those answers. So I, and some of you might remember from your CDT, which we didn't have to take this year, thankfully. But last year you'd take it, what, 3 or 4 times. You might remember seeing I on the CDT. If you did really well in your CDT, it starts giving you information that you might not have known how to solve yet. I stands for an imaginary number whose square is 1. Okay, so I itself, and you want to write this down, is equal to the square root of -1. If we were to type in the square root of -1 in our calculator, it will say error. You're not allowed to have a negative under the square root because your calculator only deals with real solutions, not imaginary solutions. Now, what this says is that the square, and this should say -1. This is a typo. The square is -1. So I squared is -1. Because if we square I and we square the square root of -1, we'll get back to -1. So these are the 2 things that you want to memorize in regards to your imaginary numbers. Those are the 2 most important pieces of information. And then an imaginary number itself is any number of the form a plus bi, where a and b are real numbers and b cannot equal 0. So for example, 2 plus 3i, that's a complex number or an imaginary number. Simplifying square roots using I. So just like we did with our answers in the section 5.5, we'll have to reduce the radical just by breaking it up into perfect squares. But you're also going to see negatives this time. So the first thing that you're going to want to do is remove the negative from underneath the radical and then replace it with an I. So whenever you take this negative and bring it outside, it does not become a negative, it becomes an I square root of 8. And that's technically because you can break this up into be the square root of -1 times the square root of 8, and then the square root of -1 is I. But I usually just get rid of the negative and put an I in the front. So you don't have to write that every time. And then you'll reduce 8 just like we normally do. So remember, when you're reducing a radical, you always want to use your perfect squares. So your 1, 4, 9, 16, 25, 36, etc. So we break this into 4 and 2. Square root of 4, square root of 2. Take the square root of 4, which is 2. Now, usually instead of writing I2, we'll write 2i, just kind of standard form, almost like how we don't write x2, even though I is not a variable. It's standing for something, but 2i root 2. It's typically how you'd see that final answer. If you left the I in the front, I probably wouldn't care, but that's how you see it. So the next one, again, our I would come out, the I square roots of 12. Now, if there was not a negative underneath there, we would just reduce it as normal. And then 12 we would break down into 4 and 3. Square root of 4 is 2. Becomes an outside number, so now we'll have 2i square root of 3. See if you guys can try C and D. All right, who can tell me what they got for C? Ashley? Very good. We should have made this I, bringing our negative out, times the square root of 9 times the square root of 6. Those are the two numbers that multiply back to get us 54, one of them being a perfect square. Taking our perfect square and then rewriting it in kind of a normal form. Then how about D? Gary?
6i.
Very good. This one is a perfect square, so it just becomes, yes, you could break it down into 9 and 4, but both of those are perfect squares. So if it's a perfect square, just take it, and the answer is just 6i. No square roots left. Very nice. Okay, complex numbers, again, have an imaginary and a real part. So they're written as a sum, a plus bi. A is standing for the real part of the number. Bi is representing the imaginary part of the number. And these are called complex numbers instead of real numbers. They have a real and an imaginary. So again, you can see the real numbers would be a plus 0i if b were to be 0, because then it was really just a real number. But imaginary numbers can be written in this form. So when we're simplifying these, first of all, make sure you read the directions so that your final answer always looks like this. So for example, if you got 7i plus 2 as your final answer, you have to make sure you flip it around so that it's in standard form, because they want it to be real plus imaginary. So you'd have to rearrange this to be 2 plus 7i. A lot of students on their quiz forget to do that and always like a half point. So just make sure the directions will tell you and remind you to do that. Just make sure you read them. So when you're doing these, you want to simplify the radical part first. You could rearrange it first as well, but typically we're going to simplify the radical. So this would become I square root of 9. And then we take the square root of 9, which is just 3. So this would be 3i plus 6. Again, we want it in the form a plus bi, so we are going to then flip this stuff around and make it 6 plus 3i instead of 3i plus 6. Next one, we'll simplify this radical part first. So it'll be negative, nope, it'll be I, taking the negative out. What would I break 18 down into? Yep, 9 and 2. You would never, ever, ever pick 6 and 3. Because 6 is not a perfect square and 3 is not a perfect square, so it would just leave you in a dead end. You wouldn't have anything to simplify. So I always want one of those numbers to be a perfect square. So then we'll get 3, square root of 9 is 3. So now I have 3i square roots of 2 plus 7. And we do need to flip that around so that the real part I also don't care if you were to write it as 7 plus 3 square roots of 2i. Either one is fine by me. You'll see it both ways with an answer key, but these are all being multiplied together, so the order in which you write them doesn't actually matter. Okay, for C, obviously taking out our negative, putting an I in front. What should I break 48 into? Garrett? 4 and 12 will work, but it will yield a multiple step problem. John? 16 and 3 would be your best bet. If you do 4 and 12, obviously 4 would be 2. You'd have to break the 12 down into 4 and 3, and then multiply those numbers at the end, which is fine, but just a lot of people forget to keep going. So if you pick the biggest square root, perfect square that goes in, it's a little easier. So we'll get 4i square roots of 3 plus 3. And then lastly, we'll switch that around. So 3 plus either 4 square roots of 3i or 4i square roots of 3. Now, the whole reason, again, I said we're learning this is that we are going to see answers to our quadratics that may look like this. Instead of having a real solution, they'll have an imaginary solution. And again, that's when if we were on the graphing calculator, our graph would look like this. And there's no way to do it on the graphing calculator because your graphing calculator can only do real solutions. So on the back, we are going to see a bunch of problems here that can all be used by square rooting. Okay, remember, square rooting is useful whenever you're missing the bx term. had some of these on our quiz last week. It just always happened that this number under the square root was positive instead of being a negative. So that's the only difference today. Okay, so just like we've done in the past, we're going to go ahead and isolate our x squared. So the first thing you would do to isolate this is undo addition with subtraction. Zero minus 100 is negative 100. Now, some of you made the mistake on your quiz of square rooting like at this point. You cannot square root until you get x squared by itself. So you'd first have to undo multiplication with division. Negative 100 divided by 4 is negative 25. If that weren't to go in evenly, we would just leave it as a fraction, right? And then we could square root both sides. And now we will square root both sides. What do I have to remember to add in when I add in a square root sign? So that I get my two answers. What do I always have to add in? Caleb? Plus or minus. So square rooting a squared, those cancel out, we just get x, equals, we put in our plus or minus, we have the square root of negative 25. Well, the negative would come out to be an I, and then the square root of 25 is just 5. So our final answer should be x equals plus or minus 5i. If you really wanted to, you could put 0 plus or minus 5i to write it as a complex number, but it doesn't say that we have to write these in a plus bi form. All right, next one. And you could, I should say, you can also factor out a 3 first if you really wanted to, like a GCF. But because it's in the form that can be square rooted, that's where I usually just go straight to square rooting instead of trying to factor. Sometimes you can factor, but typically with our complex answers, you're not going to be able to. So we would subtract 48. We would then divide by 3. To get x squared equals negative 16. And then we'll square root both sides. Inserting our plus or minus, which quite a few of you will be kicking yourself when you do get your quiz back. So miss 1 point if you don't have a plus or minus, because that's one answer that's missing. What would this be simplified? Garrett? 4i. Good. Plus or minus 4i. See if you guys can try C and D on your own with the square root. Okay. You probably want to split it up and make it into the square root of 1 over the square root of 4. And then if these weren't perfect squares, we'd have to rationalize the denominator. However, the square root of 1 is just 1, and the square root of 4 is just 2. So we're able just to simplify those without having to rationalize. So your final answer here should be plus or minus 1/2 I, or I over 2. So just make sure, and I saw a couple of you making the mistake of doing in your head 2 divided by 8 is 4 instead of 1/4. But I would suggest reducing it first. Now some of you might have done this, square root of 2/8, and then you would have to rationalize that. It's going to get you the same answer at the end of it. Square root of 16 is then 4, and then you can reduce 4/8 to be 1/2. So if you didn't realize that you should reduce the fraction first, and you went straight to rationalizing, it'll work just a little bit, sometimes harder. All right, the last thing is graphing in the complex number plane. So we've done graphing in just like an XY plane. We've done it in 3-dimensionals, X, Y, and Z. This is graphing in a complex number plane, so that this axis is now called your real axis. The real part of the number. This is your imaginary axis. So instead of being an x-axis and a y-axis, we have a real axis and an imaginary axis. So this one, what they've graphed up here is the equation 3 minus 4i. So you almost read it as if it's like a coordinate, like 3 comma negative 4 is basically how you graph it. So they went from 0, 0, the origin, they went over 3, and then they went down 4 to 4i. Does that make sense? If it were 3 plus 4i, we would go up to 4i and put a point. And these would just be coordinates, so you'd want to make sure that they're in standard form. They also have us finding the absolute value of the complex number, which, if you remember, an absolute value is the distance typically from 0 on a number line. Like if I said the absolute value of -5, it's +5, and that's because it's just on a number line. If you're finding the distance from 0, 0 in a coordinate plane, you're technically using the Pythagorean theorem. So if you knew this was 3 units long and this was 4 units long, you can find the distance from the origin, which is the absolute value, by completing the Pythagorean theorem. Now, since every single time you're doing this, you're going to be solving for C, what they've done is they actually solved the formula for C without plugging numbers in. Okay, you could plug in 3 and 4, and you'll get 5. But just to come up with a general formula so you don't have to do Pythagorean theorem, how can I solve this equation for C? What would I have to do to both sides to get rid of the square? Okay? Square it again. I would get c to the 4th. Square root. So you'll get c equals the square root of a squared plus b squared. Technically plus or minus, but when you're looking at the distance, how far something is distance-wise, you're not going to have a negative distance. So we would just take the positive square. So this is the formula to find the absolute value of a complex number. All right, now the first one they have us graphing, notice that it is not in standard form. Standard form is a plus bi, and right now it just says 5i. So technically that must be 0 plus 5i. Okay, so that means that you're going 0 left or right, and we would just go up to 5i on the axis, the point. Now, for this one, to find the distance from the origin, you could just actually count because it's a vertical space, so it's 5 units away. But just to show you, if you were to use the formula, just so you have it in your notes, we would, of course, plug in that a is 0 and that b is 5. And you will get 5 back. But if the point is just on either one of the axes, the real or the imaginary, you could just count the number of spaces. But in case it's not, you'll want to use your formula or Pythagorean theorem if you prefer. They asked us to graph and find the absolute value. So the graphing is this, the absolute value is. Okay, the next one to graph this, we have 6 minus 4i. So we'll go to 6 on the real axis, and we'll go down to negative 4i and put our point. And then to find the absolute value, you can either just use the formula, or let's suppose you're on your exam and you forget the formula. You can just create a right triangle and plug into a squared plus b squared equals c squared if you prefer. 6 squared plus negative 4 squared equals c squared, and you'll get the answer. You'll just have to do a little more work. The version that we have here just makes it already solved for c. So a would be 6, b would be negative 4. You do not plug in the I, just the b value. So we would get 6 squared plus negative 4 squared. You want to square each of the numbers to get 36 and 16. Add them together to get 52. And then we would want to reduce this radical if possible. What could I break 52 down into, one of them being a perfect square? Is 4 going evenly? Should be saying yes. We should be getting 4 and 13. And that would get me 2 squared of 13. All right, see if you can try the closure questions, just asking you to simplify And I do want you to make sure your final answer is in the form A plus BI. While I pass out your homework. Let's get two more, pull up to the board, do the closure. Rayleigh, you could do A. And Sierra's not here. Abby Wayman, B. You actually don't need the plus or minus, but it's okay. Alright. Because we didn't solve that. So this morning were the hot ticket items for homeroom.